Good afternoon. My name is Jeliazkova. I'm co-owner of SME IdeaConsult Ltd based in Sofia, in Bulgaria. The focus of this talk is Introduction to Similarity Assessment and Approach pursued by Gracious project for estimating nanoform similarity. Why Similarity Assessment of Nanoforms? Like a guidance on QSR and grouping of chemicals, and specifically the 2019 appendix for nanoforms, indicates that looking for similarities in physical properties, toxicokinetic behavior and fate, and ecotoxicological behavior between different nanoforms may be possible to substantiate the assumption of similar hazard properties between different forms of a substance. The guidance suggests using physical properties and or in vitro screening methods, so it doesn't provide details on methods to estimate similarities. This is not really an exception compared to the guidance on similarity for both substances. However, to facilitate read-across for nanoforms, the partners in Gracious project are exploring different methods and compiling recommendations. The findings will be published in a white paper and a series of use case publications. First, let's have some definitions adopted by the Gracious Similarity Task Force. A property can be a basic physical parameter, for example, size, surface area, shape, surface treatment, required to identify a nanoform. Or it could be a property to describe an aspect of nanoform interaction with the immediate surroundings, for example, reactivity or attachment efficiency. A scalar descriptor is a single number accompanied by units of measurements, for example, nanometers. Examples are median of particle size distribution or lowest observed adverse effect level for the dose response curve in inhalation toxicity. A data matrix is a matrix containing all and only the descriptors required by the IATA to a specific hazard. The role of the similarity assessment is to help taking a grouping or read-across decision about the candidate group members. The main message here is to convey is that we assume we have compiled a data matrix and we perform a similarity assessment based on this data matrix. This slide shows the structure of the data matrix for particular hypothesis. It includes properties, size, specific surface, long deposition, dissolution, reactivity, and inflammation, each with one or more scalar descriptors. For example, for dissolution, we have dissolution rate and half time. We can then use the entire data matrix on only the four properties marked with crosses, which the four properties which expert identified as best one for this particular hypothesis. Once we have identified the properties, we can apply different similarity methods. This slide illustrates perhaps the simplest way to calculate similarity by x-fold, basically the ratio between two values, the largest value divided by the smaller value of two scalar descriptors. We can look at quickly soluble zinc oxide NM110, which is a benchmark material in this case, which has a dissolution half time very low, which is indicated on the left side. And on the right side, the zinc oxide is on the second row on the right side. We have the pairwise similarity matrix, where each cell represents similarity value between pair of materials. For example, zinc oxide NM110 and titanium dioxide NM105. Two types of cereals and then barium sulfate and two iron oxides. The second iron oxide, nanoform B, has a very high dissolution half-time and hence is very different. Then this is indicated in the similarity matrix with red color and the x-fold value on the maximum x-fold value of 15,000. Apart from x-folds, there are many ways to calculate similarity, and these are defined by distances or similarity index. Let's have a look at a familiar definition for distance on a map. The distance between Sofia and Madrid on a straight line, the yellow line on the picture, is 250 kilometers. This could be considered a two-dimensional distance. Its length can be calculated using the length of the blue and the green line by the Pythagorean theorem. Of course, if you assume the Earth is flat between these 2 points. And the length of the green and the blue lines are one-dimensional distances. You could imagine these are not the only possible way to calculate distance between Sofia and Madrid. For example, the driving distance will be much longer, about 3,000 kilometers. In general, a distance between 2 points is the length of the path between the 2 points, and the path doesn't need to be a straight one. Now go back to the distances between numerical properties. Here is an illustration of different distances between point A and B, defined on the plane with descriptors x and y. The length of the blue straight line is the Euclidean distance. The red line defines another distance, which is known as Manhattan distance. On the right, the length of the blue line defines the two-dimensional Euclidean distance between the zinc oxide and barium sulfates using the reactivity descriptor on y-axis and inflammation descriptor on x-axis. Once we have the multidimensional distance calculated between each pair of nanoforms, we can populate the pairwise similarity matrix, where each cell corresponds to the integrated similarity across all relevant properties between pair of nanoforms. As already mentioned, there are many ways to calculate similarity between scalar descriptors, and here we show Euclidean distance on the first column, again Euclidean distance on the second column, but on using transform data, and finally x-fold on the third column. The first row of matrices shows the pairwise similarity matrix for dissolution rate. The second row shows the pairwise matrix for half-time dissolution, half-time. And half-time x-fold matrix is the same as shown previously. And it can be noted again that NM110 zinc oxide benchmark materials is also prominently different than other materials, but the values, the color shade are not exactly the same. And please note there is a difference between the first and the second column of matrices, even if they both use Euclidean distance. The matrices in the first column use the original data, while for the second column, the descriptors were first normalized and log transformed. Why it's important to normalize and transform the descriptors? First, normalization means all the descriptors are scaled into the same range, usually between 0 and 1. This is important, especially when using multidimensional distances. Otherwise, descriptors spanning large range will dominate other descriptors used in the multidimensional distances. The need of a log transformation or a similar transformation might be less intuitive, but its goal is to transform skewed distributions like the one we have on the left, the blue one on reactivity descriptor, to a normal distribution, more or less normal one. The log transformation is not the only one to be used. The transforms as Box-Cox or Yau-Johnson transform can be used instead of logarithmic with the same goal. It's also important to include the representative test materials for each property, otherwise we'll not be covering the entire possible range, entire relevant range for the property, and our results will be skewed. Here, an example of similarity of in vitro toxicity is demonstrated using 5 different methods: Euclidean distance with log transform data, x-fold, rsync, OWA-based similarity, and Bayesian factor similarity. The latter two are new methods developed by gracious partners. They'll be described in methodology manuscripts which are currently under preparation. All algorithms now confirm the choice of benchmark materials, which are not similar to the case studies. For example, look again at the second row where zinc oxide NM110 is almost everywhere shown in red. Ranking in most algorithms are consistent, while numerical threshold of acceptable similarity need to be different per algorithm, but can be made to result in the same groupings. And this figure also illustrates the importance of data transformation toward normal distribution when using Euclidean distance, using either a log transform, Box-Cox, or Yau-Johnson one. Preliminary results on limits of acceptable similarity are presented here. This is a result of gracious similarity task force. As indicated in the previous slides, these thresholds are different per algorithm, but can be set up to result in the same ranking. With this, I'd like to thank for your attention and will be happy to questions. Thank you.
Hello and welcome. My name is Richard Cross. I'm a researcher here at the United Kingdom Centre for Ecology and Hydrology, and today I'm going to be talking about the environmental case studies for similarity, grouping and read across that we developed within the Gracious project. Now you will have seen Vicky, Agnes and Nina's presentations before this, so I don't want to go into too much detail about the specifics of what grouping means. Suffice to say that as a recap, grouping is a general approach that allows us to assess more than one chemical at once. And importantly, when we consider nanoforms, more than just the chemical identity should be considered. Other properties need to be discussed. And that's because a nanoform may also have a specific size, shape or surface chemistry, as well as the chemical identity of the material itself. Now I'm going to give you a brief overview of the environmental hypotheses that have been developed within the Gracious project. We have a range of general hypotheses that have been developed. Those in orange are highlighted, which are hypotheses for where they go, for the environmental fate of the particles. And they're based around the dissolution rate and dispersion stability of those nanomaterials and the various outcomes for grouping which arise from the combination of those two properties. In blue, these are hypotheses which are related to biopersistence and chemical transformations, whilst in green, these are actually the hypotheses which we've been dealing with specifically at UKCEH, which is looking at coating durability against biodegradation as a way of grouping nanoforms with different surface treatments. As well as the general hypotheses, we also have some compartment-specific hypotheses for those in sediments and in soils. Now, as you will have seen from the introduction to the IATAs in an earlier presentation, what I'm going to do for the environment is go through a few examples about how we've used existing information to inform the thresholds in decision nodes in these IATAs. I'm going to use EG1 as an example of this. Now, this was the hypothesis which delivers various grouping outcomes based on the balance between the dissolution rate and the dispersion stability of your nanoforms in the aquatic environment. Now, the Gracious IATAs guide collection of the evidence that you need to accept or reject this grouping hypothesis. And importantly, that IATA specifies the most relevant tests to make that decision. Now, if we zoom in on the blue box down at the bottom here, what we can see is how our grouping by where they go, so this is the environmental fate of your nanoform, identifies both the relevant compartment for assessment, the form of the exposure, and the apical hazard endpoints of concern. So Gracious has identified a number of key decision nodes that identify what the hazard endpoints are that are relevant based on the fate of the nanoform in that environment. So, for example, it might identify whether a particle remains as a particle or dissolves into its solutes, and which of these is responsible for toxicity. Another example can be whether it identifies aquatic or sediment toxicity as being of concern. Now, to quantify the cutoffs and thresholds that are required for dissolution rate and attachment efficiency in this hypothesis, work by Mesters, published in 2019, did a sensitivity analysis for the simple box for nanomodeling, modeling nanoparticle stability in this generic aquatic environment. And it identified a threshold of around 10 to the minus 4 for attachment efficiency. And when you're below this threshold, most of the particles remain free in dispersion, so you have a stable dispersion of your nanoform. However, once you go beyond this threshold, heteroaggregation and attachment dominate the particle fate, so your nanoform becomes less stable as the attachment efficiency increases, and you might lead to sedimentation and identification of sediment toxicity as being relevant for these particles, for example. So this sensitivity analysis has been performed across a range of environments, allowing us to identify thresholds in red, above which your PEC, your predicted environmental concentration, may increase or decrease with that change in transformation rate or change in attachment efficiency. Now, when nanoforms are actually beyond this threshold, they enter a range where the PEC is sensitive to changes in these properties. When you're in these range, for example, those highlighted in blue here, a category approach to read across could be used to predict PEC on the basis of a regular trend. Alternatively, as we saw in Nina's presentation earlier, similarity assessment on individual properties of the nanoforms grouped in this applicability range could be used as part of a read-across justification. So I'm now going to give you a detailed example using the case study that we were testing at UKCEH, which is grouping nanoforms based on the resistance of surface modifications to biodegradation. And here's just a list of some of the people who were involved in this work, partners with us at UKCEH, but also at LATAT in Spain. Now, the rationale for this grouping hypothesis is that there are a likely near infinite number of coating nanoform combinations, especially if you take into account that you can have the same coating material if it's a polymer, but it might have different chain lengths or different surface coverage as well. Now, this means that it's simply too diverse to test every possible combination. However, we should not assume that if a coating differs between nanoforms that you cannot group, because this would be too restrictive. This is exactly the kind of case that grouping might be useful in allowing us to reduce the testing burden across different nanoforms. So first of all, we have to define our hypothesis. Well, we know that surface treatments may modulate the nanoparticle behavior and toxicity in the environment. However, we also know that these surface treatments may be lost. And in this case, if we have a surface treatment which is degraded in the environment, and it is no longer present at the surface of the material, that would allow nanoforms with ostensibly different surface treatments to therefore be considered similar on the basis of a similar low durability of these surface treatments. So they no longer are involved in driving the fate and hazard of these particles. Alternatively, you could have nanoforms where the surface treatment persists but is not toxic and does not change the toxic profile of these particles. In this case, nanoforms with different durable surface treatments may still be grouped according to other IATAs if it is found that they are similar according to both where they go and what they do. I.e., this means that if you have two particles with different surface treatments, if, for example, the attachment efficiency and the dissolution rate doesn't differ between those two particles, they may still be grouped by that generic hypotheses that I described earlier. There is a third case where the surface treatment persists but is also toxic. And in this case, nanoforms might be grouped for where they go, so you might be able to read across for predicting the environmental concentrations of these nanoforms in various environmental compartments. However, you cannot group for where they do, as specific toxicity of the surface coating must be considered in their risk assessment. To support this hypothesis at UKCEH, we have developed a tiered testing strategy to answer this question over whether the surface treatment is biodegradable. Now, to do this, we've optimized and adapted a well plate-based MT2 screening assay that can screen for whether the surface treatment chemicals are biodegradable. Now, what's important when you have these tiered testing strategies is that the lower tiers should be predictive of your higher tier test answers, and in some cases you can get a result which is sufficient to answer the decision node. However, in other cases, your lower tier test outcome may trigger higher tier testing if a decision cannot be reached on the basis of that lower tier outcome. So the principle behind the tests that we've developed and optimized at UKCEH is that we take the MT2 biolog microplates And this is a colorimetric carbon utilization assay in which we inoculate our plates with microbes isolated from sewage sludge. And then we introduce our test substances as well. And by monitoring the colour development, this acts as an indicator of microbial respiration and organic molecule biodegradation. And from this, we can calibrate against a reference carbon source and calculate the percentage of your chemical that was biodegraded within that well. The aim of this is to use this assay as a screening approach to identify organic surface treatments that may be biodegradable, and those from which assessment may benefit from escalation to a higher tier test. So we needed to validate our screening assay by comparing the outcomes that we got from the MT2 assay we developed at UKCEH against the outcomes and results you would get from the standard OECD 301 method, which was performed by our partners at LATAT. Now, we've tested 20 common chemicals and used the OECD 301 test to calibrate thresholds for our MT2 assay. So one example of this is that we found that citric acid is correctly identified by both the MT2 assay and the OECD test as readily biodegradable. So one question that we have is, can a threshold for percentage biodegradation in our screening MT2 assay be defined for readily biodegradable substances? Now, citric acid was a benchmark for our readily biodegradable coating, but for our non-biodegrading substances, something like PVP, we've identified as, again, successfully being identified both by the MT2 screening assay and the OECD as a non-biodegrading substance. Now, the aim of our MT2 assay is to be a precautionary screening step. So where we see positive biodegradation, we need to have good certainty that biodegradability is possible. Whereas whilst we see no biodegradation, that may actually be a cause for escalating to a higher tier test. So here is a summary of the results that we have so far, comparing between our tier 1 test in the left-hand column and our tier 2 test, which is the OECD test, in the right-hand column. And to summarise, we have 15 complete comparisons to date, and 12 of these results are in good agreement. For 4 substances, we have outstanding data. 2 of these were insoluble, and so weren't suitable for the MT2 assay, and 2 interfered with the test, thus requiring further method development. However, of the data that we have so far, it does indicate that the MT2 assay does deliver a precautionary grouping decision successfully. And this is because within our comparison and our calibration against the OECD results, we found 3 false negatives. So this was where your tier 1 did not identify biodegradation, which was then observed in your tier 2. However, we saw no false positives. So we never got a result where we saw biodegradation in the MT2 assay, but observed no biodegradation in our OECD assay. So that's nice, because that does mean that this MT2 assay is precautionary, where if we see a result, a positive response in the MT2 assay, we know that a positive response would also be observed in the OECD test. However, we know that if we don't see biodegradation in our MT2 assay, this could be a trigger for escalating to a higher tier test to see whether this is a false negative or whether there actually is no biodegradation of that chemical. So to recap and summarise, general environmental and compartment-specific grouping hypotheses have been developed, and the thresholds for these IATAs have been informed by existing modelling efforts where possible to allow us to answer decision nodes in these IATAs. Specifically for our example of coating degradation, an IATA for this grouping hypothesis, based on the durability of your organic surface treatments, has been developed. And we've also introduced a screening tier 1 assay, adapting the MT2 plate colorimetric test, and we successfully employed this to screen for biodegradation of organic surface treatments, acting as a tier 1 assessment for this decision node in our IATA. So thank you very much, and I look forward to the discussion session at the end of today. Thank you.